All right, this is my first attempt, so if this gets uploaded, congrats, because this is attempt number 1, and that means I did this in one take. Anyway, welcome to today's Wednesday video lecture where we will be going over things like periodic families, Lewis structures, valence electrons. We're going over all those things. Some of them you've already talked about with me, either live or on Edmentum or on a video or whatever, but some of this will be new information to you. So please make sure you get your notes out, you pay attention. If you notice attached, I've given the periodic table and this worksheet that I'm about to be, or not worksheet, but this sheet that I'm going to be walking through. Hopefully now you guys see what I'm working through, which is just this little topics-based thing just to keep us on track. We've got, I'll give you a little preview. We've got 1, 2, 3, 4, 5, like 7 of these, okay? So won't take us too long, hopefully about under 20. That's what we're going to shoot for. But let's go ahead and get started. So, perfect. First thing I want to talk about, periodic families, right? Also, sometimes you'll see families and substitute for the word groups. It makes sense for what we're talking about. There's 4 periodic families that I really want you guys to know. And those 3, I'm going to write them here, and then we're going to look at a periodic table together. The first one is the alkali metals. Second one is this looks very similar, but it is different. Alkaline, see that I-N-E, earth metals. Why did I just switch to all caps there? Sometimes my brain doesn't even make sense. So we've got the alkaline earth metals. We have, oh wow. How do I want to do this? I want to go up. I want to do this. I want to go bada bing, bada boom. And we're going to slide. Rats. Let's try that again. Aha, now we got it. I'm going to slide it over. And then the other 2 that I want to talk about are the halogens and the noble gases. Okay, so keep those 4 names in mind as we, if you need to pause, write it down, whatever, as we jump over to our periodic table. We have 4 periodic families that we're mainly going to be working with or focusing on here. And the first of which that we wrote down was those alkaline metals. I'm sorry, not alkali metals, not the alkaline earth. So we're going to first look at those alkali metals, okay? And the main thing that I want you all to do here is be able to identify which ones I'm talking about. When I say alkali metals, I'm talking about group 1A. So all of those elements in group 1A are considered alkali metals. If you look at my periodic table up here or at any colored periodic table, you'll see that these elements are organized based off of, or they're color coordinated often based off of whether they're metal, non-metal, or metalloids. So these are obviously metals. Is hydrogen a metal? No, it is not. So it gets excluded from that alkali metals. Sometimes you'll see it grouped in there just because it's in that same 1A. It shares similar properties, but of course it's not a metal. So those are your alkali metals. I want you to be able to identify those, and what we know about valence electrons should tell you how many valence electrons alkali metals have. It's 1. And then the second group, let's switch over to a red pen here. The second group I want to talk about are your very similarly named alkaline earth metals. Your alkaline earth metals. Those are your alkaline earth metals. All group 2A elements are your alkaline earth metals, okay? Alkaline earth metals are like alkali metals in that obviously they're both metals. They're both highly reactive. Alkali metals are more reactive because they have a closer number to a full octet. We'll talk about that more later. But alkaline earth metals have 2 valence electrons. These guys want to get rid of those valence electrons to have a full octet shell. We'll talk about how that happens once we intro ionic bonds, but I want you to know those. The other 2 that I want you to know, let's switch. Am I going to run out of colors? Let's go for halogens. Let's go. Ooh, that's too big. For halogens, we're going to color it in blue. But halogens are those guys right there. Your group 7A elements are your halogens. So how many covalent, or not covalent, how many valence electrons would they have? 7, of course. Okay, so from fluorine all the way down to acetine, and I don't even know, what did they end up naming that? Tennessine? Okay, cool. From fluorine all the way down to tennessine, those are your halogens. And then the next halogen that we're going to see in here, or not halogen, the next family that we're going to identify, and I guess let's do galaxy colored, why not? So for this next group or family, those are the noble gases. Does gases have two S's? I don't think so. I don't know. If it does, then my bad. I misspelled that. 8A, noble gases, group 8A. These are them right there. Those noble gases are the pinnacle or the idea that all electrons or atoms are trying to be like. What do I mean by that? Well, how many valence electrons do noble gases have? They have 8 valence electrons. What you're going to learn later today is 8 is the desired number of valence electrons for most every atom, and we'll talk about why. But valence electrons, 8 is the desired number. So noble gases is your primo, your prime, your cream of the crop. They're not very reactive because they don't need any more electrons. So they don't need any to get to 8, and they don't want to get rid of any because then they won't be at 8 anymore. So those are the 4 families you need to be able to identify. 1A, alkali metals, 2A, alkaline earth metals, 7A, halogens, and 8A, noble gases. Okay, so jumping back over here, those are the periodic families you should be able to identify. Now, we're going to talk and we're going to pivot and move to the 3 or 4 different orbital blocks or energy sublevels or orbital shapes, your S, P, D, and F orbitals. Now, with those orbitals, first things first, on page 183 is a really good picture in your textbook if you want a visual of how these are arranged. But these sublevels, right? So I call them energy sublevels is because we defined earlier that N equals whatever, that would be your energy level. And so you can have as many sublevels as is equivalent to your level. What do I mean by that? Well, if you are in the second energy level, you can have up to 2, or you will have 2 sublevels. Okay, if you're in the third energy level, you'll have 3 sublevels, etc. Okay, so that's just a little side bit there. But what are these sublevels? Well, they simply, we got to head back to the periodic table for this bit. I'm going to erase what I just wrote over here. But looking at our periodic table, every element in the periodic table can be categorized in one of these sublevels. Let's identify what I mean by that. Okay, so every electron, right, has a path around the nucleus. And the shape of those paths is categorized into this S, P, D, and F, right? It has to do with Latin, where they got those values. I'm sorry, where they got those numbers. But there's basically 4 blocks we can break the periodic table into: the S block, P block, D block, and F block. So really simply, I'm going to identify those 4 blocks here. Let's see how good Mr. Lee's tracing skills are. Ooh, I'm going to use my shapes feature. Objects, ink to shape. Perfect. Let's see if I can do this. So first sublevel or block we're going to look at. Come on now. Oh, wow. You guys, I'm telling you, writing on this thing is impossible. What is it going to shape to? Did you not snap to a shape? Yeah, ink to shape. Okay, maybe it's because my shape wasn't like a standard shape. So let's try this one more time. Well, you guys are getting a really good visual on this S block element, on these S block elements. But basically this first, oh, will you snap? Oh, look how beautiful. Okay, so this first little, perfect right there. No, can you get bigger? Excellent. So this first blue section over here, those are our S block elements. An element in the S block has a, or the electrons that are in that S block will have a certain shape. We're going to talk about that more, but I'm just going to break down the presence of these different blocks. So that's your S block. Group 1A and 2A are your S block elements. Okay. Fun fact, hydrogen or helium is also considered to be part of that S block because even though helium's organized over here because it has a full valence shell because it only has 2, it's technically one of those S block elements. So just have that visually in your brains. Okay. Next, we have our P block. Okay. So you have your S block and your P block. P block are these elements down here. Wow. Let's hope this snaps well for me. Bam. Oh, beautiful. I love it. I love it. So your P block elements. Oh no. We're just going to do that. You can get the idea. From boron through, what are we calling this these days? Oganesson, right? So I can't even pronounce half of these things. So these P elements down here, those are considered your P block elements. Okay, from group 3A to group 8A, those are your P block elements because those electrons found in that sublevel have a certain shape. And we're going to talk again more about sublevel shape, but right now I just want you to identify these different blocks. And then the third energy sublevel, or AKA, let's undo that, AKA blocks here, the third that we have, I'm going to go a little faster this time. Wow. I'm telling you, this is impossible to do. Oh, so nice. Anyway, this third group right here, these D block elements, okay? Those are your D block elements. So we have S, P, and D, those transition metals, those are your D block elements. But if you notice right here, there's this little asterisk. It jumps from 57 to 72 and from 89 to 104. That's because you have down here, and I guess I'm just using black because that's my only color left. You have down here what we call your F block elements, okay? So let's knock this out again. Boomtown, okay? You have your D block elements, or sorry, F block elements. So we'll just do that to represent those down there. These are the F block elements, rarely used in our class, but it's important to recognize where they are and what they are. So you have four main blocks that we break our periodic table down into: S block, P block, D block, and F block. Well, what does that mean? Okay, let's jump back over here now that we've identified them. What that really means is that these energy levels, whenever we look at a Bohr model, for certain atoms found in those blocks, those shapes that we draw as circles, they really have a lot crazier shapes. And if it's in the S block, it has a certain type of shape. If it's in the P block, it has a certain type of shape. So that's what we mean by that. You're going to see that in your textbook, but I need you to recognize that you can have up to, and this will help visualize it. So you can have up to as many sublevels for an energy level as is the value there. So what do I mean by that? If n equals 1, that's our first energy level, right? Or this first period. You can only have one sublevel, the S block, okay? Because remember, helium's part of that. When n equals 2, you can have two sublevels. You can have S and P elements. Now, this is where it gets a little controversial, because when n equals 3, you may say, Mr. Lee, it only looks like it has two. But some of you guys heard me say this, that this group of elements right here, from scandium all the way to zinc, that technically is the beginning of the third energy level, even though it's in the fourth principal energy level. We're going to talk about that more on Thursday and Friday when we talk about quantum numbers. But that technically, that three sublevels would technically include S, P, and D. And then fourth, again, fourth now starts to include F, even though it's down here, right? So your fourth energy level would be S, P, D, and F. Don't get too confused by that right now. Just a little side piece of information. You're not going to be asked a question like that on a quiz. So those are our orbital blocks or energy sublevels. Let's backtrack a little bit, start with something really simple that we all remember, and that's valence electrons. What did we define valence electrons to be? We defined them to be the electrons found in the outermost orbital of an atom, right? We also learned the shortcut to find valence electrons. It's equal to the group number for what? For my representative elements, aka my A block elements, right? Or my A group elements, for those representative elements. So that 1A, 2A, 3A, 4A, 5A, 6A, 8, 7A, 8A, those are equivalent to the number of valence electrons you will find for that atom. Now, another term that you may hear thrown around, whether it's in a textbook or in a video, is this term, the octet. What does the term octet mean? Well, first let's break it down. Latin root oct means 8, and so that's ultimately where we're going to go from there. We know that there are 8 desired valence electrons for any atom. And so again, this is going back to what I talked about earlier about our noble gases, but 8 is the desired number of valence electrons. And some of you say, well, Mr. Lee, what about in the third energy level? You have 18 electrons, not 8. Well, whenever we're talking about valence electrons and how many we desire, we subtract our D and F block elements, right? So what I mean by that is the third group can have up to 18 electrons, right? Third group can have up to 18 electrons. Well, if you subtract your D block elements from that because those are your transition elements, then it would be what? It would be really 8, right? So that's the desired number, even if you're in the third group. And then continuing on, if you're in the fifth group, you may say, okay, Mr. Lee, if you're in the fifth group, that's the energy levels doesn't get larger after 5. But again, you would subtract your number of F and D. Ultimately, take my word for it, we want 8 valence electrons no matter what atom we are. That's the goal, right? That's the dream. That would be considered stability. You'd have exactly how many you need, okay? So 8 valence electrons, that's our desired number. So that's where you get this term octet coming from, okay? So octet, we're gonna write atoms, desire 8. I'm just gonna write valence electrons like that, because it's considered most stable. Nothing more, nothing less. Because it's considered most stable. Energetically, that is, right? Because it's all about energy. So that is considered the most energetically stable. And so when you're bonding, right? When an atom bonds with another one, whether it's ionic or covalent, that's ultimately why they're bonding. Right? They're bonding because they want 8 electrons. So if by doing so, if by bonding up with the nearest carbon, that'll give them 8 electrons or a full valent shell of electrons, that's what they want to do. So that's why things bond and why things react. Another example that I always use when I'm in person is, let's say I have $7 and a cheeseburger costs $10. How many dollars do I need? I only need $3 to achieve $10. Now, say Timmy has $3, I have 7, right? It's more advantageous for us to pool our money together and have 10 and share that 10 than for both of us just to be without it, right? Even if it may be an unfair share and that I'm paying more and Timmy's only paying 3, this is not a perfect analogy, but it shares why or how things bond together, right? If you had 7 valence electrons and there was an element with 3 valence electrons, now we're going for 8, so let me use a more relevant example. If you had 6 valence electrons and there was an element with 2, you'd say, hey, you have 2, I have 6. We can make something work out here to where you give me those 2 electrons. Now I'll have 8, my desired number. And by getting rid of those 2 electrons, you now have the lower number, right? So you had 2 in your valence, and so now you have a full outermost shell because you got rid of those valence electrons. So that's this idea of the octet, is that how does an atom reach 8 valence electrons? So knowing that, I do want to introduce just this very simple idea of the coordination site, okay? Basically, because we're going to talk about Lewis dot structures, so let me actually start there, and then we'll come back to the coordination site. Lewis dot structures are an incredibly simple way of showing visually an atom with its valence electrons. All you do is you write the atomic symbol. So let's do carbon here for the first one. So you'd write the chemical symbol and then how many valence electrons it has, you'd write them as dots. You may also see this written as electron dot diagram. So let's take carbon, for example. Carbon has how many valence electrons? Well, it's in group 4A, 1, 2, 3, 4A. So I know it has 4 valence electrons. So if carbon has 4 valence electrons, I ultimately want to draw 4 dots around carbon. Now, this thing called the coordination site, this is how that Lewis dot structure looks because of these coordination sites. Most atoms and almost all A group atoms that we're dealing with have only 4 coordination sites, or 4 areas around that atom as we visually represent them, where bonds or electrons can be found, right? And so we have those 4 coordination sites, and so they're really just up, down, right, left. So we write those 4 dots just around like that. And you may say, Mr. Lee, what if you have more than 4 electrons? That's when you start pairing up. So let's look at the next atom on the periodic table, nitrogen, okay? Nitrogen has 5 valence electrons because it's in group 5A. I should have written these out earlier. 3A, 4A, 5A, 6A, 7A, 8A, 1A, 2A. Okay, so nitrogen is in group 5, so it has 5 valence electrons. So to draw the Lewis dot structure for nitrogen, you start by filling each of those coordination sites first, if you can. 1, 2, 3, 4, you can. Now you have an extra one. Where does that go? Then you start pairing. So that would be the appropriate Lewis dot structure for nitrogen because it has 5 valence electrons. You've shown it as 1, 2, 3, 4, 5. Let's keep going. Let's do another one for lithium. Okay, lithium is in group 1A. How many valence electrons does lithium have then? 1. That's the Lewis dot structure for lithium. Yes, to answer your question, if you wrote it like this, that would be fine. Doesn't matter where your coordination site starts, just as long as it's evenly balanced. What do I mean by that? Oxygen's a great example. Okay, oxygen has 6 valence electrons, so I go 1, 2, 3, 4, 5. You can do it like that. You can write it as 6 as long as there's 2 over there. I normally like to balance it just for symmetry and visualization's sake. You could write it like that, or you could write it like that. As long as you have the appropriate number, I don't care. And they're following that coordination rule that you fill each one first and then you add on the other one. That is how you represent Lewis dot structures. So if on a quiz or something, I had you draw a Lewis dot structure for me, take a picture of it and send it in, you could do that. I could say draw a Lewis dot structure for fluorine. All you'd have to do is find out which group fluorine's in. It's in group 7A. So you know fluorine has 7 electrons, or 7 valence electrons, I should say. So you'd go 1, 2, 3, 4, 5, 6, 7. Boom. That's valence electrons. That's Lewis dot structures. That's octet rule. That's coordination sites, right? I'm going to write down here 4 for most representative elements. Just so that you have a definition or something right down there. Okay, you have 4 coordination sites for most representative elements. Now, the last thing on this list, Lewis dot structures for molecules. We haven't even defined what a molecule is, but some of you guys know what a molecule is. It's basically, right, a combination of multiple non-metal atoms, okay? We're going to talk more about classification of metal, non-metal, but ultimately that's just going to be in your reading. You'll recognize there's certain periods and certain groups that have more metals and non-metals than others on the periodic table. That's just from recognizing colors and how to follow along there. So molecules, one of the most common that we see is hydrogen chloride, or I'll write it as we'd normally see it, right? Hydrochloric acid, hydrogen mixed with chlorine, okay? So with hydrochloric acid, we could write this as a Lewis structure. We just need to first write the individual atom, right, as a Lewis structure. So hydrogen has 1 valence electron, boom. Chlorine has 7, boom. We're going to talk about this more when we talk about covalent bonds and ionic bonds, but I just want to give you an idea of what we're doing here, okay? Hydrogen is an exception to the rule. Hydrogen does not desire 8 electrons. It only desires 2. Why is that? Because hydrogen, what's its nearest noble gas? Helium, right? Helium over here. Helium's its nearest noble gas, and how many valence electrons does helium have? It only has 2. This is an exception to the rule. It only has 2 because look, what's its atomic number? It's atomic number 2. So a neutral helium would only have 2. So hydrogen really only desires 2 instead of an octet. It has what's called a duet. Hydrogen really only desires 2. Chlorine desires 8. So long story short, what they do is they say, hey, let's share these lone pairs. It'll be like you have 2 and it'll be like I have 8 and we'll both be stable. I just wanted to give you an introduction to what these look like. This is kind of a little bonus add-on here, but like water, okay? If you broke down what we're looking at with water, it's H2O. How many hydrogen atoms? 2. How many oxygen atoms? 1. Let's draw their Lewis structures. 1, 1, and then we know oxygen to have 6, right? We know oxygen to have 6 valence electrons. So these guys would share, wow, I did not mean to do that. These guys would, oh, okay, we're just doing it again, huh? We're just gonna be that way. Let's try it one more time. Excellent. These guys would share, and these guys would share. Because then hydrogen would be happy because it would have the 2 that it wants, and oxygen would be happy because by sharing with 2 hydrogens, you now have 8 for hydrogen or for oxygen's valence. So that's why you see a water molecule written like that. You have the bond representing 2 electrons, okay, shared between atoms. And then you have these valence electrons written as lone pairs. Now, if you're confused by this, don't worry about it. This is just a little add-on so that when we get there in a week or 2, you'll know what we're talking about. But ultimately, what I need you to know from today is how to draw a Lewis structure, okay, for any neutral atom. I need you to know the octet rule, right? That every electron desires 8 valence or every atom desires 8 valence electrons when possible. Valence electrons, how we organize the orbital blocks or the shapes of these orbitals on the periodic table and those periodic families. So there it is. So your periodic table, if you have one at home, mark it up, make it look organized however you need it to be. But that's it for today. I don't know exactly how long this video was, but it hopefully wasn't too long and it hopefully wasn't too confusing. So it looks like I got this done in one take. Yeehaw. I'll see you guys tomorrow or Friday live. Bye.